Hello there, and welcome to another gentle journey through the cosmos, where mysteries unfold like distant flowers blooming in the endless garden of space. Tonight, we're embarking on a tale as old as the solar system itself, a story of wandering ice giants that have danced through the heavens for billions of years, capturing human imagination and carrying secrets from the very dawn of our cosmic neighborhood. Before we drift into this celestial adventure, I'd love to know where in the world you're watching from. And have you ever been lucky enough to spot a comet streaking across your night sky? Perhaps you remember the excitement of Hale-Bopp in the 1990s. Or maybe you caught a glimpse of the recent visitor Suchenshan Atlas that graced our skies just months ago. Fitting, isn't it, that we're here together under the same starlit dome that has witnessed these icy travelers for millennia? If you find this voyage through space and time soothing or perhaps intriguing in that gentle way that makes you want to learn more, I'd be ever so grateful if you gave the video a like and maybe subscribed. It helps this little corner of cosmic calm reach other stargazers who might need a peaceful pause beneath the infinite sky. Now, I do hope this isn't so fascinating that it keeps you awake, but if it does, well, at least you'll have learned something about the most beautiful vagabonds in our solar system before you drift off. So settle in, perhaps with a warm cup of tea, and let's begin. Because somewhere between ice and fire, between the ancient past and the eternal dance of celestial mechanics, lies the gentle story of comets. Imagine, if you will, a snowball the size of a mountain drifting silently through the cold darkness of space for thousands, perhaps millions of years. It tumbles slowly, end over end, a frozen relic from when our solar system was nothing more than a swirling cloud of dust and gas waiting patiently in the outer reaches where sunlight is but a distant whisper. This is how our story begins, not with a bang, but with a quiet, patient journey that spans eons. These wandering ice giants, as we might call them, are among the most ancient objects in our solar system, leftovers from that primordial time. 4.6 billion years ago, when the sun was just beginning to ignite and the planets were still forming from cosmic debris. They are in essence frozen libraries containing the chemical signatures of our very origins, each one a time capsule that has travelled unimaginably vast distances to eventually grace our skies with their ethereal beauty. The word comet itself comes from the ancient Greek word kometes, meaning long-haired star, a rather poetic description from our ancestors who watched these mysterious visitors appear, seemingly from nowhere, trailing their magnificent luminous tails across the heavens, like cosmic calligraphy written against the dark canvas of night. They didn't know what these apparitions were, of course, but they recognized something profound in their appearance, something that spoke to the deeper mysteries of existence. What makes a comet so utterly captivating is this remarkable transformation that occurs as it approaches our sun picture, that mountain-sized snowball we imagine drifting through the frigid outer reaches of the solar system for millennia. It's a dark, forbidding chunk of ice, mixed with dust and rocky particles so cold that even the hardiest microbes couldn't survive on its surface. The temperature hovers around -200 degrees Celsius, colder than the harshest Antarctic winter by several hundred degrees. But then something wonderful begins to happen as this ancient wanderer's elliptical orbit brings it closer to our star. The sun's warmth begins to work its gentle magic on the comet's surface. The ices don't melt in the traditional sense. Instead, they sublime, transforming directly from solid to gas in a process that creates the most spectacular light show in our solar system. This is where the magic truly begins, where a humble chunk of dirty ice becomes something that can inspire awe across entire civilizations. As the comet continues its approach, the sublimating gases carry with them tiny particles of dust, creating what astronomers call the coma, a vast, glowing atmosphere that can expand to become larger than the planet, Jupiter. Imagine that for a moment, this cloud of gas and dust surrounding the tiny nucleus can grow to dimensions that dwarf our entire world, The scale is almost impossible to comprehend, yet there it is, dancing delicately in the solar wind, like cosmic silk caught in an invisible breeze. But the coma is just the beginning, as solar radiation pressure and the charged particles streaming from the sun interact with this expanding atmosphere. Something even more magnificent occurs, the formation of the comet's tail. Or more accurately, its tails, because a comet actually develops two distinct tails each, with its own personality and behavior. The first is the dust tail, composed of those tiny particles liberated from the nucleus. As the ice sublimates, this tail appears yellowish or white to our eyes, and curves gently away from the sun, following the comet's orbital path. Like a cosmic contrail, it can stretch for millions of kilometers, creating those sweeping arcs that have inspired artists and poets throughout history. The second tail is even more ethereal. The ion tail formed when ultraviolet radiation from the sun strips electrons from gas molecules, creating charged particles that glow with an otherworldly blue light. This tail always points directly away from the sun, regardless of the comet's direction of travel, creating sometimes dramatically different orientations as the comet swings around our star. It's as if the sun is a cosmic hairdryer, blowing these charged particles straight back in a perfectly aligned stream. What's particularly enchanting about these tails is that they're always directed away from the sun, which means that as a comet travels away from our star, after its closest approach, it's actually traveling backwards relative to its tail. Imagine a cosmic swimmer doing the backstroke through space with their hair streaming out in front of them. It's a delightfully counterintuitive image that speaks to the elegant physics governing these celestial dances. The nucleus itself, the solid heart of the comet, is a surprisingly modest affair compared to the spectacular displays it creates. Most comet nuclei are just a few kilometers across irregular lumps of what scientists rather unpoetically call dirty snowballs. But this description hardly does justice to these remarkable objects. They're among the darkest things in our solar system, reflecting only about 2 to 4% of the light that hits them, making them darker than fresh asphalt. This darkness comes from a coating of organic compounds and dust that accumulates on the surface as the comet makes repeated journeys around the sun, creating a kind of cosmic patina that tells the story of countless solar encounters. It's rather like an old leather journal that's been weathered by time and travel, each mark and stain, a testament to the adventures it has witnessed. The composition of comets reads like a recipe from the early solar system. Water ice makes up the majority of the nucleus, typically around 80%, but mixed in are frozen carbon monoxide, carbon dioxide, methane and ammonia, along with silicate dust and organic compounds that are quite literally the building blocks of life. These are the same materials that may have been delivered to the early Earth billions of years ago, seeding our planet with the ingredients necessary for life to begin. It's a humbling thought that these wandering ice giants might be our cosmic ancestors, in a very real sense, carrying within their frozen hearts the very substances that eventually gave rise to oceans and perhaps even the first primitive life forms. They are not just beautiful celestial visitors, but potentially the gardeners who planted the seeds of life throughout the solar system. As we watch a comet grace our skies, we're witnessing a process that connects us directly to the formation of our solar system. Each particle of dust streaming from the nucleus, each photon of light scattered by the coma, is part of an ancient story that began before the Earth existed. It's a story written in ice and dust in the patient orbits that carry these objects through the cosmic deep, and in the brilliant displays that occur when they venture close enough to our sun to awaken from their frozen slumber. The beauty of this process is that it's happening right now, somewhere in our solar system. There are comets beginning their long journey toward the sun, while others are retreating back into the cold depths, having completed their spectacular performances. Some are making their first recorded visits to the inner solar system, while others, like the famous Halley's Comet, are old friends returning on schedules more reliable than most earthly appointments. What strikes me as particularly wonderful about comets is how they embody both permanence and change. They are ancient objects that have remained essentially unchanged for billions of years. Yet each time they approach the sun, they transform themselves, shedding material and creating new displays. They are simultaneously timeless and ephemeral, cosmic and intimate, visible to the naked eye, yet originating from distances so vast that light itself takes months or years to travel from their home regions to our Earth. This duality perhaps explains why comets have always held such a special place in human imagination. They appear suddenly in our skies like cosmic messengers, bringing news from the outer darkness. They grow brighter and more spectacular over weeks or months, then gradually fade as they retreat back into the depths of space. Their visits are rare enough to feel special, yet predictable enough that we can anticipate and prepare for them. In many ways, comets are the perfect ambassadors. From the deep solar system, they bring us samples of materials from the very edge of our cosmic neighborhood. Materials that have been preserved in the cosmic freezer for billions of years. They allow us to study the conditions that existed when our solar system was young, and they do so with a beauty and grace that makes even the most complex astrophysics feel like poetry. Tonight, I'd like to take you on a journey to two of the most extraordinary neighborhoods in our solar system, places so distant and mysterious that until relatively recently, we could only theorize about their existence. Yet these regions are the true homes of our wandering ice giants, the nurseries where comets are born, and where they patiently wait between their spectacular visits to our inner solar system. Let's begin with a voyage to the edge of everything we know, a place so far from the sun that if you were standing there, our star would appear as nothing more than a particularly bright point of light, indistinguishable from the other stars scattered across the cosmic canvas. This is the Oort cloud, named after the Dutch astronomer Jan Oort, who first proposed its existence in 1950. Though we've never directly observed it, we know it must be there, like a vast, invisible sphere surrounding our entire solar system. Imagine, if you will, a snow globe, but instead of a quaint winter scene inside, there's our entire solar system, the sun, all the planets, their moons, the asteroid belt, everything we consider local and familiar. Now imagine that this snow globe is surrounded by a cloud of icy particles so enormous that it extends halfway to the nearest star. The Oort cloud is thought to contain billions, perhaps trillions of these frozen objects, drifting in the cosmic deep like seeds waiting for the right conditions to bloom. The scale of this region is almost beyond comprehension. It begins roughly 2,000 times farther from the sun than Earth is and extends outward to perhaps 200,000 times our distance from the sun. To put that in perspective, light from the sun takes about 8 minutes to reach us, but it would take nearly 3 years to reach the outer edges of the Oort cloud. We're talking about distances where our familiar solar system becomes nothing more than a tiny bright dot in an ocean of darkness. What's particularly fascinating about the Oort cloud is how spherical it is. Unlike the relatively flat disk of our solar system, with its planets orbiting in roughly the same plane, the Oort cloud surrounds us from all directions above, below, and to every side. This is why long-period comets, those that take hundreds or thousands of years to complete their orbits, can appear from any direction in our sky. They're not confined to the ecliptic plane where we find planets and asteroids, but can dive toward the sun from the cosmic equivalent of any angle. The objects in the Oort cloud lead remarkably peaceful lives. For the most part, they drift slowly through the near absolute cold of interstellar space, barely moving relative to each other like cosmic icebergs in a frozen sea. Most will never venture closer to the sun than they are right now, content to remain in their distant orbits for billions of years. But occasionally, something disturbs this tranquil existence. Perhaps a passing star comes relatively close to our solar system, its gravitational influence creating tiny perturbations in the Oort cloud, like ripples on a pond, or maybe the gravitational tug of the galaxy itself. As our solar system orbits the Milky Way, center creates subtle changes in the cloud's structure. These gentle influences can nudge an object just enough to send it falling inward on a journey that will take thousands of years to complete. When one of these distant wanderers begins its long fall toward the inner solar system, it's embarking on perhaps the most dramatic transformation possible in our cosmic neighborhood. It starts as a dark, frozen chunk, barely distinguishable from a large asteroid. But as it approaches the sun, it gradually awakens, becoming first a faint fuzzy object, then a spectacular comet with flowing tails that can be seen from Earth. But the Oort cloud isn't the only source of our celestial visitors. There's another region much closer to home, though still unimaginably distant by earthly standards. The Kuiper belt stretches beyond Neptune's orbit, beginning about 30 times farther from the Sun than we are, and extending to perhaps 50 times our distance. It's like a second asteroid belt, but instead of a rocky debris, we find a treasure trove of icy objects. The Kuiper belt is home to some fascinating residents, including the dwarf planet Pluto, which we've reclassified from planet to dwarf planet as we've learned more about this distant realm. It also contains thousands of smaller objects, sometimes called Kuiper belt objects, or trans-Neptunian objects, that range in size from tiny pebbles to bodies hundreds of kilometers across, unlike their distant cousins in the Oort cloud. These Kuiper belt residents tend to orbit the Sun in the same general plane as the planets, creating what astronomers call the short-period comets, those that complete their orbits in less than 200 years. These are the comets we're most familiar with, including the famous Halley's Comet, which visits us every 76 years or so. What's particularly intriguing about the Kuiper belt is that we can actually observe some of its residents directly with our most powerful telescopes. We've even sent spacecraft to visit them. NASA's New Horizons probe flew past Pluto in 2015, giving us our first close-up views of this distant world, and later visited another Kuiper belt object called Arakoth, providing unprecedented insights into these ancient remnants of solar system formation. The objects in both the Oort cloud and Kuiper belt are essentially time capsules preserved in the cosmic freezer. For 4.5 billion years, they contain materials that formed when our solar system was young, before the planets had finished growing. Before life appeared on Earth, they're samples of the primordial solar nebula, the disk of gas and dust from which everything we know eventually condensed. When we study comets, we're essentially doing archaeology on a cosmic scale, examining artifacts from the very dawn of our solar system. The water ice we find in comets might be similar to the water that eventually filled Earth's oceans. The organic compounds could be precursors to the molecules that made life possible. It's as if each comet is a message in a bottle thrown into the cosmic ocean billions of years ago, finally washing up on the shores of our awareness. What strikes me as particularly wonderful about these distant realms is how they challenge our sense of what belongs to our solar system. When we look up at the night sky, we see the moon, the planets, perhaps the space station passing overhead, and we think of these as our cosmic neighborhood. But our true neighborhood extends so much farther than most of us realize. The Oort cloud makes our solar system nearly 4 light years across, almost reaching halfway to the nearest star, Proxima Centauri. In a very real sense, the boundary between our solar system and interstellar space is not a sharp line, but a gradual transition zone where our sun's influence slowly fades and the gravitational pull of other stars begins to dominate. This vast extended family of icy objects also tells us something profound about planetary formation. When our solar system was young and the planets were still growing through a process called accretion, many of these icy bodies were scattered outward by the gravitational influence of the giant planets, particularly Jupiter and Saturn. Like cosmic billiard balls, they were flung into the outer darkness, where they've remained ever since. Some scientists believe that this scattering process was crucial for life on Earth. The same gravitational interactions that sent comets to the Oort cloud and Kuiper belt also may have delivered water and organic molecules to our planet during a period called the Late Heavy Bombardment, roughly 4 billion years ago, when Earth was pelted by asteroids and comets. It's a remarkable thought that the very process that banished these objects to the edge of the solar system may have been essential for creating the conditions that allowed life to flourish on Earth. The comets we see today are the survivors, the objects that escaped this ancient cosmic shuffling and now occasionally return to remind us of those violent but ultimately creative early days. As we've learned more about these distant populations, we've also discovered that they're not entirely stable over very long time scales. The sun's motion through the galaxy occasionally brings us closer to other stars or dense molecular clouds, whose gravitational influence can disturb the Oort cloud, sending showers of comets toward the inner solar system. These events happen on timescales of millions or tens of millions of years, but they may explain some of the patterns we see in Earth's geological record periods, when impact craters seem to be more common, suggesting that our planet was experiencing more frequent visits from these icy travelers. It's another reminder that our solar system is not an isolated island, but part of a dynamic galactic community. The story of how humans first began to understand these celestial visitors is as fascinating as the comets themselves. For most of our history, these mysterious apparitions were viewed with a mixture of awe and terror, appearing suddenly in the night sky like cosmic omens, carrying messages that ancient civilizations struggled to interpret. In ancient China, astronomers kept meticulous records of what they called broom stars. Because of the way their tails swept across the heavens, Chinese court astronomers believed these visitors carried profound significance, often interpreting their appearance as warnings of political upheaval or dynastic change. The brightness of a comet, its position relative to certain constellations, even the direction of its tail were all carefully noted and analysed like a cosmic form of divination. The ancient Greeks and Romans had their own interpretations, often seeing comets as harbingers of doom or divine displeasure. When a bright comet appeared, it might foretell the death of a ruler, the outbreak of war, or some other calamity. This wasn't entirely unreasonable thinking from their perspective. After all, these strange objects appeared without warning, blazed across the sky for weeks or months, then vanished as mysteriously as they had arrived. What else could they be but messages from the gods? One of the most famous historical connections between comets and earthly events occurred in the year 1066, when what we now know as Halley's Comet appeared in the skies over Europe just months before the Norman conquest of England. The comet was seen as such a significant omen that it was depicted in the famous Bayeux tapestry, where Norman and Saxon nobles point at it with expressions of wonder and concern, as if acknowledging its role in the unfolding drama. But Halley's Comet had been visiting long before the Normans arrived. Chinese records describe its appearances going back over 2,000 years, each return carefully documented by generations of skywatchers who didn't yet understand that they were observing the same object returning on a predictable schedule. They simply knew that every few generations this particular bright visitor would grace their skies. The shift from seeing comets as omens to understanding them as natural phenomena was gradual and required some of humanity's greatest minds. Tycho Brahe, the Danish astronomer, made careful observations of a bright comet in 1577 and determined that it was much farther away than the moon. This was revolutionary thinking because it challenged the ancient Greek idea that comets were atmospheric phenomena occurring in the upper reaches of Earth's air. But it was Edmund Halley who truly revolutionized our understanding of these objects in the late 17th century. Halley was a friend and contemporary of Isaac Newton, and he applied Newton's new laws of motion and gravitation to the problem of comet orbits by carefully studying historical records. Halley noticed that bright comets had appeared in 1531, 1577 and 1682, roughly 76 years apart. With remarkable insight, Halley proposed that these were not three different comets, but the same object returning periodically on an elliptical orbit that carried it far beyond the outer planets and then back toward the Sun. He predicted that it would return again in 1758. And when it did, appearing almost exactly when and where he had calculated it, would the scientific revolution gained one of its greatest triumphs. Suddenly, comets were no longer mysterious omens, but clockwork mechanisms following predictable paths through space, governed by the same physical laws that kept planets in their orbits. It was a profound shift in human understanding, transforming these celestial visitors from supernatural messengers into natural phenomena that could be studied, analysed, and even predicted. The return of Halley's Comet in 1758 was observed by astronomers across Europe, who marvelled at the precision of the prediction. Here was proof that the universe operated according to mathematical principles that human minds could comprehend and use to peer into the future. It was perhaps the first time in history that scientists had successfully predicted the return of a celestial object decades in advance. As telescopes improved during the 18th and 19th centuries, astronomers began to discover more and more comets. Some were periodic visitors like Halley, returning on predictable schedules. Others appeared to be making their first journey through the inner solar system on orbits so elongated that they wouldn't return for thousands or perhaps millions of years. Each new discovery added pieces to the puzzle of what comets actually were and where they came from. Some astronomers noticed that comet tails always pointed away from the sun, regardless of which direction the comet was traveling. This observation led to early theories about solar radiation pressure and what we now call the solar wind, the stream of charged particles flowing outward from our star. The development of photography in the 19th century revolutionized comet observation. For the first time, astronomers could capture detailed images of these objects, studying their structure and evolution over time, rather than relying solely on sketches and written descriptions. They discovered that comets often had multiple tails, and that these tails could change dramatically as the comet moved through its orbit. One of the most spectacular comets of the 19th century was the Great Comet of 1811, which remained visible to the naked eye for over a year. Its appearance coincided with a particularly good vintage in the Champagne region of France, leading to bottles of 1811 champagne being called comet wine, as if the celestial visitor had somehow blessed the grape harvest. By the early 20th century, astronomers were beginning to develop modern theories about comet composition. The idea that they were dirty snowballs, mixtures of ice and rocky material, began to take shape. As scientists studied the spectra of light emitted by comet tails, they could identify specific molecules, water vapor, carbon monoxide, cyanide, and other compounds that told the story of what these objects were made of. The space age brought unprecedented opportunities to study comets up close, rather than observing them from millions of kilometers away. Spacecraft could actually visit these objects, analyze their composition, and even land on their surfaces. The first close encounter came in 1986, when an international fleet of spacecraft met Halley's Comet during its most recent return. The images sent back by these missions were revelatory, showing Halley's nucleus to be a dark, irregular object, about 15 kilometers long and 8 kilometers wide, shaped rather like a peanut and covered with a crust so black it reflected less light than charcoal jets of gas and dust erupted from specific locations on the surface, creating the spectacular displays visible from Earth, but originating from a relatively small and surprisingly dark source. Perhaps the most ambitious comet mission was the European Space Agency's Rosetta probe, which spent over a decade journeying to Comet 67P, Churyumov-Gerasimenko, arriving in 2014. Rosetta became the first spacecraft to orbit a comet, accompanying it as it approached the Sun and watching its transformation from close quarters. The mission included a small lander called Philae, which actually touched down on the comet's surface, though it bounced several times before coming to rest in a shadowed area that limited its operational time. The data returned by Rosetta and Philae provided unprecedented insights into comet composition, structure, and behavior, confirming many theories while raising entirely new questions. One of the most intriguing discoveries was that the water in Comet 67P had a different isotopic signature than Earth's oceans. suggesting that comets like this one may not have been the primary source of our planet's water. Other comets, however, have shown water signatures much closer to Earth's, indicating that the story of how our oceans formed is more complex than previously thought. Modern comet hunters use a combination of ground-based telescopes and automated sky surveys to discover new visitors. Some are professional astronomers working with sophisticated equipment, while others are dedicated amateurs who spend clear nights scanning the skies with telescopes in their backyards. The thrill of discovery remains as powerful today as it was centuries ago, when a comet hunter spots a fuzzy patch of light moving slowly against the background stars. The process of confirming a new comet discovery involves careful observation over several nights to establish its orbit and determine whether it's truly a new object or perhaps a known comet. Returning after a long absence, each confirmed discovery adds to our growing catalogue of these objects, helping astronomers understand the populations and dynamics of the outer solar system. Some of the most exciting recent discoveries have been comets visiting from interstellar space objects that formed around other stars and somehow found their way into our solar system. These interstellar visitors offer tantalizing glimpses of planetary systems beyond our own, carrying samples of materials that formed in entirely different stellar environments. The study of comets has also revealed important information about the early history of life on Earth. Many of the organic compounds found in comets are precursors to biological molecules, suggesting that these visitors may have delivered some of the raw materials necessary for life to begin. It's a humbling thought that the carbon in our bodies or the water we drink might have arrived on Earth aboard one of these ancient travelers. As our understanding of comets has evolved, so too has our appreciation for their role in the broader story of our solar system. They're not just beautiful curiosities, but active participants in an ongoing process of planetary evolution, still delivering materials from the outer solar system to the inner regions, still capable of surprising us with unexpected behavior and new discoveries. The more we learn about these wandering ice giants, the more we realize how much we still don't know. Each new mission, each improved telescope, each detailed observation adds pieces to a puzzle that spans the entire history of our solar system, from its formation 4.5 billion years ago to the present day and likely far into the future. What strikes me as particularly wonderful about our evolving relationship with comets is how it mirrors humanity's broader journey of understanding the universe around us. We've moved from fear and superstition to curiosity and scientific investigation, from seeing omens in the sky to recognizing fellow travelers sharing the same cosmic neighborhood. Yet even with all our modern knowledge and sophisticated instruments, comets retain their power to inspire wonder. When a bright comet appears in our skies, it still draws crowds of people outside to gaze upward and contemplate their place in the cosmos. It still represents something profound about the nature of existence. The fact that we live in a universe full of ancient wanderers, carrying stories from the very beginning of time. These celestial visitors remind us that our solar system is not a static, unchanging place, but a dynamic environment where objects formed billions of years ago continue to move and evolve. They connect us to the deepest past, while simultaneously pointing toward an infinite future filled with discoveries yet to be made tonight. I'd like to share with you some of the most remarkable encounters between humanity and these cosmic wanderers, stories that span centuries and continue to unfold in our modern age, each one adding layers to our understanding of these magnificent travelers and their profound influence on both science and the human imagination. Let's begin with perhaps the most famous comet of all, one whose name has become synonymous with celestial punctuality, Halley's Comet, named after Edmund Halley. Though he certainly didn't discover it has been gracing our skies with remarkable regularity for over 2 millennia. What makes Halley so special isn't just its predictable 76-year orbit, but the way it has woven itself into the fabric of human history, appearing at moments of great significance and inspiring generations of observers. The earliest recorded sighting of what we now know to be Halley's Comet dates back to ancient Chinese astronomers in 240 BCE, who described a broom star sweeping across the heavens, But it was the comet's appearance in 66 CE that truly launched it into the annals of history, arriving just as the First Jewish-Roman War was beginning, leading some to interpret it as a celestial commentary on earthly conflicts. Perhaps no appearance of Halley's Comet is more famous than its visit in 1066, when it blazed across European skies, just months before the Battle of Hastings. The Norman conquest of England was forever linked to this celestial visitor immortalized in the Bayeux tapestry, where figures point skyward at the comet with expressions of awe and foreboding, as if acknowledging its role as a harbinger of change. What's particularly fascinating is how different cultures interpreted the same celestial event. While Europeans saw an omen of political upheaval, Chinese astronomers recorded it as part of their systematic sky-watching program, treating it as one of many astronomical phenomena to be carefully documented and analyzed. It's a beautiful example of how the same cosmic event can be filtered through entirely different cultural lenses. Halley's Comet continued to appear throughout the centuries, each return adding to its legend. In 1531, it was observed by the astronomer Petrus Appianus, who made detailed drawings of its changing appearance as it approached and receded from the sun. His sketches show how the comet's tail always pointed away from the sun, a crucial observation that would later help scientists understand the forces shaping these celestial displays. But it was the comet's return in 1682 that proved most significant for the development of modern astronomy. This was when Edmund Halley observed it and began his careful analysis of historical records, realizing that the bright comets of 1531, 1577, and 1682 might actually be the same object returning on a predictable schedule. Halley's prediction that the comet would return in 1758 was more than just a scientific calculation. It was a test of humanity's ability to understand and predict celestial mechanics. When the comet appeared almost exactly as predicted, it marked a triumph of mathematical astronomy over superstition and folklore. Suddenly, the heavens seemed less mysterious and more comprehensible. The comet's most recent visit in 1986 was perhaps its most thoroughly studied appearance in history. An international armada of spacecraft, including Giotto Sakigake Suisei and the two Soviet Vega probes, rendezvoused with Halley, providing our first close-up views of a comet nucleus. The images revealed a dark potato-shaped object about 15 kilometers long, spewing jets of gas and dust from active regions on its surface. These missions transformed our understanding of comet structure, showing that beneath the spectacular displays visible from Earth lay relatively small, dark objects, more like flying mountains than the ethereal beings they appeared to be from a distance. The nucleus of Halley's Comet was darker than coal, reflecting only about 4% of the sunlight that hit it, a revelation that surprised many scientists. But Halley is far from the only comet to capture human imagination. The Great Comet of 1811 remained visible to the naked eye for an extraordinary 17 months, becoming one of the most observed celestial events of the 19th century. Its appearance coincided with Napoleon's invasion of Russia, leading some to connect the comet with earthly disasters. Though, of course, the timing was purely coincidental. More recently, Comet Hale-Bopp became the comet of a generation when it appeared in the mid-1990s, visible to the naked eye for an unprecedented 18 months, and reaching a brightness that made it easily seen even from light-polluted cities. Millions of people around the world stepped outside to witness this cosmic visitor, making it perhaps the most widely observed comet in history. What made Hale-Bopp so spectacular was its unusual size and composition, with a nucleus estimated to be about 40 kilometers across, much larger than typical comets. This gave it the ability to produce massive amounts of gas and dust, even when relatively far from the sun, creating the brilliant display that captivated observers worldwide. The discovery of Hale-Bopp itself is a wonderful story of amateur astronomy. At its finest, Alan Hale and Thomas Bopp independently spotted the comet on the same night, in July 1995. Hale was a professional astronomer conducting a systematic search, while Bopp was an amateur observer who happened to notice the fuzzy object while stargazing with friends. Their simultaneous discovery led to the comet bearing both their names. More recently, Comet Neowise graced our skies in 2020, providing a bright spectacle during a time when many people were spending more time at home. Due to global circumstances, it served as a reminder that the cosmos continues its ancient dance regardless of human affairs, offering moments of beauty and wonder that transcend earthly concerns. The story of Comet Shoemaker-Levy 9 represents perhaps the most dramatic comet encounter in recorded history. This unusual object had been captured by Jupiter's gravity and broken into multiple fragments, creating a cosmic string of pearls that eventually collided with the giant planet in July 1994. For the first time in human history, we witnessed the collision of celestial bodies in real time. The impacts of Shoemaker-Levy 9's fragments with Jupiter created fireballs larger than the Earth itself and left dark scars in the planet's atmosphere that persisted for months. It was a sobering reminder of the dynamic and sometimes violent nature of our solar system, while also demonstrating Jupiter's role as a cosmic vacuum cleaner, protecting the inner planets from potential impactors. These dramatic events have helped scientists understand that comet impacts may have played crucial roles in planetary evolution. The late heavy bombardment period, roughly 4 billion years ago, when the inner solar system was pelted by asteroids, and comets may have delivered much of Earth's water and organic compounds, setting the stage for the emergence of life. The search for new comets continues to this day, with both professional surveys and dedicated amateur astronomers scanning the skies for these elusive visitors. Automated telescopes now discover most new comets, but there's still room for the patient observer with a good telescope and an intimate knowledge of the night sky to make significant discoveries. Some of the most exciting recent developments involve comets from outside our solar system. Interstellar visitors that formed around other stars and somehow found their way into our cosmic neighborhood. These objects offer tantalizing glimpses of planetary systems beyond our own, carrying samples of materials that condensed in entirely different stellar environments. The first confirmed interstellar comet 2, Borisov, was discovered in 2019 by amateur astronomer Gennady Borisov using a telescope. He built himself. This small fuzzy object was clearly different from solar system comets, with a hyperbolic orbit that indicated it originated elsewhere and would eventually leave our solar system, never to return. Observations of Borisov revealed that despite forming around a different star, its composition was remarkably similar to comets in our own solar system, suggesting that the processes of planetary formation may be universal, creating similar types of objects regardless of which stellar system they occur in. The study of comets has also benefited enormously from space-based observations. Telescopes like Hubble and Spitzer have provided detailed views of comet structure and composition, while specialized missions have visited these objects up close. The Deep Impact mission deliberately crashed a projectile into Comet Tempel 1 in 2005, excavating pristine material from the comet's interior. Perhaps the most ambitious comet mission was the European Space Agency's Rosetta probe, which spent over a decade traveling to Comet 67P Churyumov-Gerasimenko, becoming the first spacecraft to orbit a comet and deploy a lander on its surface. The mission provided unprecedented insights into comet composition and behavior, following the object as it approached the Sun and underwent its spectacular transformation. One of Rosetta's most surprising discoveries was that the comet's nucleus consisted of two distinct lobes, connected by a narrow neck, creating a shape reminiscent of a rubber duck. This structure suggested that the comet might have formed when two separate objects gently collided and stuck together in the early solar system. The mission also revealed the incredible complexity of comet activity, with jets of gas and dust erupting from specific locations on the surface. In response to solar heating, these active regions changed over time as different areas of the nucleus were exposed to sunlight during the comet's rotation, creating a dynamic and ever-changing display. Rosetta's lander, Philae, provided direct measurements of the comet's surface. discovering organic compounds that are precursors to biological molecules. These findings supported theories that comets may have delivered some of the building blocks of life to the early Earth, contributing to the chemical soup from which life eventually emerged. The mission also revealed that water in Comet 67P had a different isotopic composition than Earth's oceans, suggesting that comets like this one were not the primary source of our planet's water. Other comets, however, have shown water signatures much closer to terrestrial values, indicating that the story of how Earth acquired its oceans is more complex than previously thought. Modern comet hunting combines traditional visual observation with sophisticated automated surveys that scan large areas of sky, each night looking for moving objects. These surveys have dramatically increased the rate of comet discovery, but they've also changed the nature of the hunt, with most new finds being made by robotic telescopes rather than human observers. Yet there's still something magical about the moment of discovery. Whether it's a computer algorithm flagging an unusual object, or an amateur astronomer noticing a fuzzy patch that wasn't there the night before, each new comet represents a messenger from the outer reaches of our solar system, carrying information about conditions in the cosmic deep. The development of better instruments and techniques continues to reveal new aspects of comet behavior. We now know that some comets have seasons with different hemispheres becoming active as they rotate, and various regions receive sunlight. Others show unexpected bursts of activity as buried pockets of volatile material are suddenly exposed to solar heating. Some comets even exhibit what astronomers call outgassing events, where sudden releases of trapped gases create temporary increases in brightness. These events can happen unpredictably, making comet observation an ongoing adventure where established objects can still surprise experienced observers. The role of comets in popular culture has evolved alongside our scientific understanding. While ancient civilizations saw them as omens, modern society views them as natural wonders worthy of celebration. Bright comets now prompt public star parties and observing events where people gather to share telescopes and marvel at these cosmic visitors together. Social media has transformed how we experience bright comets, with photographers around the world sharing spectacular images and time-lapse videos that capture the subtle motion of these objects against the stellar background. These shared experiences create a sense of global community as people from different continents observe and document the same celestial visitor. The study of comets has also contributed to our understanding of astrobiology, the science of life in the universe. The organic compounds found in comets, along with their delivery of water to planetary surfaces, suggest that these objects may play important roles in making planets habitable. Some scientists even speculate that life itself might be able to survive within comet nuclei protected by ice and rock from the harsh radiation of space if true. This would mean that comets could potentially transport living organisms between planets or even between star systems. Though this remains a highly speculative idea, what continues to fascinate scientists is how much we still don't know about these ancient objects. Each new mission, each improved observation reveals unexpected complexities that require us to revise our theories and develop new models of comet behavior and evolution. The modern era of comet exploration is revealing these objects to be far more complex and dynamic than anyone imagined. They're not simply dirty snowballs, but intricate worlds with their own geology, weather patterns, and evolutionary histories that span billions of years. As we look toward the future, new missions are being planned to visit additional comets, sample their materials, and perhaps even attempt to deflect one slightly to test planetary defense techniques. The study of these objects continues to yield insights that extend far beyond astronomy, touching on questions of planetary formation, astrobiology, and even the future survival of life on Earth. Tonight, I'd like to share with you something that might surprise you about these celestial wanderers, something that challenges our very understanding of what it means to be a comet in the vast darkness beyond Neptune's orbit. Astronomers have recently discovered objects that behave like comets, but look nothing like the spectacular visitors we're accustomed to seeing in our night skies. These mysterious objects have been given the rather poetic name dark comets, and they represent one of the most intriguing puzzles in modern astronomy. Imagine, if you will, an object that accelerates through space like a comet pushed by invisible forces, yet shows no visible tail, no glowing coma, no obvious signs of the sublimation that creates the ethereal beauty we associate with these wandering ice giants. The discovery of dark comets began with an enigma in 2017, when astronomers detected what appeared to be the first visitor from another star system, an object they named Oumuamua, which means messenger or scout in Hawaiian. This elongated, rocky body tumbled through our solar system on a hyperbolic trajectory, clearly originating from interstellar space. But as scientists tracked its motion, they noticed something peculiar. Oumuamua was accelerating in ways that couldn't be explained by gravity. Alone, something was giving it an extra push as it traveled through space. Yet telescopes detected no signs of outgassing, no coma, no tail, nothing that would indicate the kind of sublimation that typically produces such accelerations in comets. It was as if an invisible hand was gently nudging this cosmic visitor along its path. This mysterious behavior led scientists to propose various explanations. Perhaps Oumuamua was made of unusual materials that sublimated in ways we couldn't detect. Maybe it was an artificial object, though this idea remained highly speculative, or possibly it represented an entirely new class of celestial body, one that challenged our traditional categories of asteroids and comets. As astronomers began looking more carefully at objects within our own solar system, they started finding similar examples. Small bodies that showed unexplained accelerations, but lacked the obvious cometary features. We expected to see these dark comets, as they came to be called, suggested that our understanding of the boundary between asteroids and comets was more blurred than we had realized. The implications of dark comets extend far beyond mere classification. They suggest that there may be many more active objects in our solar system than we previously recognized bodies that are slowly outgassing or shedding material in ways too subtle for our current instruments to detect directly, yet still significant enough to alter their trajectories through space. What makes these objects so fascinating is how they highlight the limitations of our observational capabilities. We've become accustomed to thinking of comets as objects that announce their presence with spectacular displays. But dark comets remind us that nature doesn't always conform to our expectations. There may be countless objects out there quietly undergoing the same processes that create visible comets, but doing so on scales too small for us to notice. The study of dark comets is being revolutionized by artificial intelligence and machine learning algorithms that can analyze vast datasets, looking for subtle patterns that human observers might miss. These computational tools are particularly well suited to finding faint objects or detecting minute changes in brightness or trajectory that might indicate previously unknown types of activity. NASA has even launched challenges inviting researchers around the world to develop better algorithms for detecting these elusive objects. The goal is to create tools that can spot comets that are too faint or too distant for traditional observational methods. It's a beautiful example of how modern technology is expanding our ability to explore the cosmos. The search for dark comets has also benefited from improvements in our space-based observatories. Telescopes operating outside Earth's atmosphere can detect much fainter objects and track their motions with greater precision than ground-based instruments. This enhanced sensitivity is revealing a population of small, active objects that would have remained invisible to earlier generations of astronomers. Some dark comets may be objects that were once more traditionally active, but have exhausted much of their volatile materials. After multiple passes near the Sun, they might retain just enough ice or other sublimating compounds to produce tiny accelerations, while no longer generating visible tails or comas. These objects could represent an evolutionary stage in comet development that we're only now beginning to recognize. Others might be composed of materials that sublime at wavelengths outside the visible spectrum, making them invisible to optical telescopes but potentially detectable with infrared or other specialized instruments as our observational capabilities continue to improve. We may discover that many objects we currently classify as asteroids are actually very subtle comets. The existence of dark comets also raises intriguing questions about the delivery of materials to planetary surfaces. If these objects are more common than we realized, they might represent an ongoing source of water and organic compounds being delivered throughout the solar system in quantities we haven't properly accounted for. This has implications for our understanding of planetary evolution and the potential for life to emerge on worlds we might not have considered habitable. If dark comets are continuously delivering materials to planetary surfaces, they could be slowly transforming the chemistry and perhaps even the atmospheres of distant worlds. The study of interstellar objects like Oumuamua has opened an entirely new field of astronomy. These visitors from other star systems carry information about planetary formation processes around different types of stars. They're like cosmic ambassadors bringing news from stellar neighborhoods we may never be able to visit directly. Each interstellar visitor represents a sample of materials that formed under different conditions around a different star. The composition of these objects can tell us about the diversity of planetary systems throughout our galaxy and perhaps provide clues about how common Earth-like worlds might be. The recent discovery of additional interstellar objects has confirmed that these visitors are not as rare as initially thought. Our solar system appears to be regularly crossed by objects from other stellar systems. Though most are too small or too faint to detect with current technology, as our observational capabilities improve, we expect to find many more of these interstellar travelers, each one offering unique insights into the processes that shape planetary systems throughout the galaxy. The study of these objects is helping astronomers understand whether our solar system is typical or unusual in the broader cosmic context. The tools being developed to study dark comets and interstellar objects are also advancing our ability to detect potentially hazardous objects that might pose risks to Earth by improving our capacity to spot small, faint objects moving through space. We're building better systems for planetary defense. This work has revealed that space is far more dynamic and populated than we previously realized. There are countless small objects moving through our solar system, many of which remain undetected simply because they're too small or too dark for our current instruments. The development of next-generation telescopes and space-based observatories promises to revolutionize our understanding of these populations. The Vera Rubin Observatory, currently under construction, will survey the entire visible sky every few nights, providing unprecedented opportunities to discover and track small moving objects. Similarly, the James Webb Space Telescope's infrared capabilities are opening new windows into the composition and behavior of comets, allowing us to study these objects in wavelengths of light that were previously inaccessible. This enhanced sensitivity is revealing details about comet structure and activity that were impossible to observe with earlier instruments. The field of comet science is also benefiting from international collaboration with researchers around the world, sharing data and coordinating observations to maximize the scientific return from each discovery. This global approach is particularly important for studying objects that may only be visible for brief periods or from specific locations on Earth. Citizen science projects are also playing an increasingly important role in comet discovery and monitoring. Amateur astronomers equipped with modern digital cameras and computer software can contribute meaningful observations to professional research programs. These collaborations between professional and amateur astronomers continue a tradition that has enriched comet science for centuries. The story of dark comets reminds us that the universe is full of surprises, and that our understanding of even familiar objects like comets continues to evolve as we develop better tools and techniques for studying them. Each new discovery challenges our assumptions and forces us to refine our models of how the solar system works. What strikes me as particularly wonderful about this ongoing research is how it demonstrates the interconnected nature of astronomical discovery. Improvements in one area, such as the development of better algorithms for detecting faint objects, often lead to breakthroughs in seemingly unrelated fields. The study of comets, both traditional and dark, also illustrates how our perspective on the solar system continues to expand. What once seemed like a relatively simple collection of planets orbiting the Sun has revealed itself to be an incredibly complex and dynamic system, filled with countless objects following intricate gravitational choreography. These discoveries remind us that we live in a universe where the familiar and the mysterious coexist, where objects that have been studied for centuries can still surprise us, and where new types of celestial bodies await discovery in the cosmic depths. As we continue to push the boundaries of what we can observe and understand about our solar system, we're constantly reminded that the story of these wandering ice giants is far from complete. Each new mission, each improved instrument, each innovative analysis technique adds new chapters to this ancient tale. The realm of dark comets represents just one frontier in our ongoing exploration of the solar system. There are undoubtedly other mysteries waiting to be uncovered, other types of objects that will challenge our categories and expand our understanding of how planetary systems form and evolve. What makes this research so compelling is how it connects the smallest details of individual objects to the largest questions about planetary formation and the potential for life throughout the universe. Every comet, whether bright and spectacular or dark and subtle, carries information that helps us understand our place in the cosmic story. The gentle persistence of these investigations, the patient accumulation of observations and measurements over years and decades, exemplifies the best of scientific inquiry. It's work that requires both technical precision and imaginative leaps, the ability to see patterns in data, and the courage to propose new explanations for unexpected phenomena. As we drift toward the conclusion of our journey through the realm of comets, it's worth reflecting on how these objects continue to serve as bridges between the familiar and the unknown, between our earthbound perspective and the vast scales of space and time that govern the universe. They remind us that we are part of something much larger than ourselves, participants in an ongoing cosmic story that began billions of years ago and will continue long after we're gone. Yet through our observations and our growing understanding, we become conscious witnesses to this ancient dance, capable of appreciating both its beauty and its profound significance. The wandering ice giants will continue their eternal journeys, carrying their frozen libraries of primordial materials through the cosmic deep, occasionally gracing our skies with their presence, and always reminding us that the universe is vast, ancient, and filled with wonders waiting to be discovered. As we stand at the threshold of a new era in comet exploration, I'd like to share with you some of the most extraordinary missions and discoveries that are reshaping our understanding of these ancient wanderers, each one revealing layers of complexity that transform these celestial visitors from simple dirty snowballs into intricate worlds with their own unique personalities and evolutionary stories. The European Space Agency's Rosetta mission, which we touched upon earlier, represents perhaps humanity's most intimate encounter with a comet. This remarkable spacecraft didn't simply fly past its target, but became a companion to Comet 67P Churyumov-Gerasimenko, spending over 2 years studying it as it approached the Sun and underwent its spectacular transformation from dormant ice ball to active comet. What Rosetta discovered was a world far more complex than anyone had imagined. The comet's nucleus wasn't a simple sphere, but rather resembled a cosmic rubber duck with 2 distinct lobes connected by a narrow neck. This unusual shape suggested that the comet had formed when 2 separate objects gently collided and merged in the early solar system, a process that may be common among these ancient bodies. The surface of 67P proved to be a landscape of remarkable diversity, with cliffs, plains, and even what appeared to be sand dunes created by the movement of dust across the comet's low-gravity environment. Rosetta's cameras captured images of boulders, some as large as houses, scattered across the surface like cosmic debris from some unimaginable construction project. But perhaps most fascinating were the active regions where jets of gas and dust erupted from the surface as solar heating caused subsurface ice to sublime. These weren't random events, but followed patterns related to the comet's rotation and the changing angle of sunlight, creating a kind of seasonal cycle on this small world. The Philae lander, though it encountered difficulties during its descent and ended up in a shadowed location that limited its operational time, still managed to provide direct measurements of the comet's surface, the first time any human-made instrument had touched down on one of these objects. The data revealed organic compounds, including some that are precursors to the building blocks of life. These discoveries have profound implications for our understanding of how life might have emerged on Earth if comets delivered not just water, but also complex organic molecules to our planet. Billions of years ago, they may have provided much of the raw material from which life eventually developed. NASA's Stardust mission took a different approach to comet exploration by actually capturing samples of comet dust and returning them to Earth for detailed laboratory analysis when the spacecraft flew through the tail of Comet Wild 2. It collected thousands of microscopic particles in a special aerogel collector designed to gently slow down the high-speed dust without destroying it. The analysis of these samples revealed that comet dust contains minerals that formed at very high temperatures near the early sun before being transported to the outer solar system, where they were incorporated into comet nuclei. This discovery challenged simple models of solar system formation, showing that there was much more mixing and transport of materials than previously thought. The Deep Impact mission demonstrated an even more direct approach to comet exploration by deliberately crashing a copper projectile into Comet Tempel 1. At high speed, the impact excavated pristine material from the comet's interior, while the main spacecraft observed the event from a safe distance. The collision created a brilliant flash visible from Earth and excavated far more material than expected, suggesting that the comet's interior was fluffier and more porous than anticipated. The spectroscopic analysis of the ejected material revealed water, ice carbon dioxide, and organic compounds, confirming that comets contain the ingredients necessary for life. These missions have also revealed that comets are not uniform objects, but have distinct layers and regions with different compositions. Some areas are rich in water ice, while others contain more carbon dioxide or other volatile compounds. This internal structure tells the story of how these objects formed and evolved over billions of years. The study of comet composition has benefited enormously from advances in spectroscopy. The analysis of light to determine what substances are present when sunlight reflects off a comet or when gases in the coma emit their own light. Each chemical compound produces a unique signature that astronomers can identify. This technique has revealed that comets contain an astonishing variety of materials, including not just the expected water ice and carbon compounds, but also more exotic substances, like hydrogen sulfide, which gives some comets a distinctive rotten egg smell, and various organic molecules that on Earth are associated with living processes. One of the most intriguing discoveries has been the detection of molecular oxygen in Comet 67P. This was completely unexpected because oxygen molecules are very reactive and shouldn't survive for billions of years in the harsh environment of space. Yet Rosetta found significant amounts suggesting that this oxygen was trapped when the comet formed and has been preserved ever since. The isotopic composition of comet materials has provided another window into solar system. History isotopes are variants of chemical elements with different numbers of neutrons, and their ratios can tell us about the conditions under which materials formed the deuterium to hydrogen ratio. In comet water, for example, varies significantly between different comets. Some comets have deuterium ratios similar to Earth's oceans, while others are quite different. This variation suggests that comets formed in different regions of the early solar system or under different conditions, and that the story of how Earth acquired its water is more complex than a simple delivery by comets. The organic compounds found in comets include amino acids, the building blocks of proteins and nucleotide bases, components of DNA and RNA. While these molecules are not alive themselves, their presence in comets suggests that the raw materials for life may be common throughout the solar system. This has led to speculation about panspermia, the idea that life or its precursors might be transported between planets or even between star systems by comets and asteroids. While this remains a hypothesis, the discovery of complex organic molecules in comets certainly makes such scenarios more plausible. The behavior of comets as they approach the Sun has also revealed unexpected complexity. Rather than simply heating up uniformly, these objects show distinct patterns of activity related to their rotation seasons and internal structure. Some regions become active, while others remain dormant, creating asymmetric jets and irregular comas. The changing activity patterns as comets orbit the Sun create what astronomers call light curves, graphs, showing how brightness varies over time. These patterns can reveal information about the comet's rotation period, the distribution of active regions on its surface, and even its internal structure. Modern computer models can simulate comet behavior, taking into account factors like the sublimation of different types of ice, the heat conduction through porous materials, and the complex gravitational effects that shape the trajectories of ejected particles. These simulations help astronomers understand observations and predict future behavior. The study of comet orbits has revealed the gravitational influence of the giant planets, particularly Jupiter, which acts like a cosmic shepherd, deflecting some comets into shorter period orbits while ejecting others from the solar system entirely. This process has been ongoing for billions of years, continuously reshaping the population of comets. We observe some comets show dramatic changes in their orbits due to non-gravitational forces. The rocket-like effect of gas and dust streaming from their surfaces can significantly alter their trajectories over time. This makes long-term predictions of comet positions challenging and adds an element of uncertainty to comet astronomy. The discovery of comet families, groups of comets that appear to have originated from the breakup of larger parent bodies, has provided insights into comet structure and evolution. These families can be identified by their similar orbital characteristics and sometimes by their composition, suggesting they share a common origin. The most famous example is the Kreutz Sungrazer family, a group of comets that follow very similar orbits, taking them extremely close to the Sun. These objects are thought to be fragments of a much larger comet that broke apart centuries ago and continue to fragment further as they make their perilous journeys around our star. Space-based observatories have revolutionized comet discovery, and monitoring the SOHO spacecraft, originally designed to study the Sun, has discovered over 4,000 comets, many of them small sun grazers that would be impossible to detect from Earth. These discoveries have revealed that small comets are far more common than previously thought. The upcoming Legacy Survey of Space and Time at the Vera Rubin Observatory promises to discover thousands of new comets and track their behavior over time. This comprehensive survey will provide unprecedented statistics on comet populations, helping astronomers understand the structure and evolution of the outer solar system. Artificial intelligence is playing an increasingly important role in comet research. Machine learning algorithms can analyze vast amounts of data, looking for patterns that human observers might miss. These tools are particularly valuable for processing the enormous data sets that modern sky surveys produce. Citizen science projects have also democratized comet discovery. Amateur astronomers around the world contribute observations and even discover new comets using relatively modest equipment, combined with dedication and skill. These collaborations between professional and amateur astronomers continue to enrich our understanding of these objects. The development of more sensitive detectors and better data processing techniques is revealing ever fainter comets and allowing astronomers to study these objects at greater distances. This improved sensitivity is showing that the boundary between active comets and dormant asteroids is more blurred than once thought. Some asteroids occasionally show comet-like activity when subsurface ice is exposed by impacts or thermal stress. These main belt comets, as they're called, challenge our traditional categories and suggest that water ice may be more widely distributed in the solar system than previously realized. The study of extinct comets objects that have lost their volatile materials through repeated solar heating provides insights into comet evolution. These dark remnants may be indistinguishable from asteroids, but their orbits often reveal their cometary origins as we look toward the future. New missions are being planned to visit additional comets, sample their materials, and perhaps even attempt to modify their orbits. These ambitious projects will continue to expand our understanding of these ancient objects and their role in solar system evolution. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is opening new windows into comet composition, allowing astronomers to study these objects in wavelengths of light that reveal different aspects of their structure and behavior. Ground-based telescopes equipped with advanced adaptive optics systems can now resolve details on comet nuclei that were previously accessible only to spacecraft. These observations provide crucial data for planning future missions and understanding comet behavior. The field of comet science continues to evolve rapidly with new discoveries, challenging established theories, and opening unexpected avenues of research. Each observation, each mission, each analysis adds pieces to the puzzle of how our solar system formed and evolved. What strikes me as particularly remarkable about modern comet research is how it connects the smallest details of individual particles to the grandest questions about planetary formation and the origin of life. Every molecule detected in a comet's coma, every isotope ratio measured in return samples contributes to our understanding of cosmic history. The gentle persistence of this research, the careful accumulation of data over years and decades, exemplifies the methodical approach that has made modern astronomy so successful. It requires both technical precision and imaginative interpretation, the ability to see patterns in complex data, and the wisdom to know when observations are challenging our assumptions. As our instruments become more sensitive and our analysis techniques more sophisticated, we continue to discover that comets are far more complex and varied than anyone imagined. They're not just ancient relics, but active participants in ongoing processes that shape the solar system. The story of comets reminds us that scientific understanding is always provisional, always open to revision based on new evidence. What we know about these objects today is vastly more detailed than what previous generations understood. Yet it's certainly incomplete compared to what future astronomers will discover. These wandering ice giants continue to surprise us with their diversity, their complexity, and their beauty. They serve as messengers from the outer darkness, carrying information about conditions in the early solar system, and perhaps about the potential for life throughout the universe. Each comet that graces our skies, whether it's a familiar periodic visitor or a first-time traveler from the outer reaches, represents a link to the deepest past and a glimpse of the cosmic processes that continue to shape our solar system. They remind us that we live in a dynamic universe where ancient objects continue to evolve and where new discoveries await those patient enough to watch and wonder. But perhaps no aspect of comet science captures the imagination quite like the ongoing search for these celestial wanderers, a pursuit that combines cutting-edge technology with the timeless human desire to discover something new in the vast darkness above us. Tonight, I'd like to take you into the world of modern comet hunting, where dedicated observers, both professional and amateur, scan the skies with patience that would make ancient astronomers proud. The art of comet hunting has evolved dramatically since the days when astronomers relied solely on their eyes and simple telescopes to spot fuzzy patches moving slowly against the stellar background. Today's comet hunters employ sophisticated digital cameras, automated telescopes, and computer algorithms that can process thousands of images each night, searching for the telltale signs of these icy visitors. Yet despite all this technological advancement, the fundamental challenge remains the same: distinguishing a genuine comet from the countless other fuzzy objects that populate our skies. Distant galaxies, nebulae, and even defects in imaging equipment can all masquerade as potential comets, requiring careful observation and analysis to separate the real discoveries from the false alarms. The most prolific comet discoverers today are actually robotic surveys, massive automated systems that photograph large swaths of sky night after night. Programs like the Catalina Sky Survey Linear and NEOWISE have revolutionized the field, discovering hundreds of new comets each year, while simultaneously searching for potentially hazardous asteroids that might pose risks to Earth. These surveys operate with mechanical precision, capturing images of the same regions of sky, separated by hours or days, then using sophisticated software to identify any objects that have moved between exposures. The computers flag potential discoveries, which are then examined by human analysts who must determine whether each candidate is truly a new comet or something else entirely. But automated surveys don't find everything. They have blind spots, regions near the sun, where their cameras cannot safely point, and they sometimes miss objects that are particularly faint or unusual. This leaves room for dedicated amateur astronomers who know the sky intimately and can spot subtle changes that might escape automated detection. The amateur comet hunter typically works with more modest equipment, perhaps a small telescope and digital camera, but compensates with deep knowledge of specific regions of sky. These observers often specialize in particular areas, returning to the same star fields night after night, memorizing the positions of faint stars and galaxies so thoroughly that any new visitor immediately stands out the moment of discovery. Whether by human observer or computer algorithm, is always thrilling, that first glimpse of a fuzzy patch where none existed before, followed by the careful work of confirming that the object is indeed moving and determining its preliminary orbit. Each new comet represents a messenger from the outer solar system, carrying information about conditions in the cosmic deep. The process of confirming a comet discovery involves multiple observations spread over several nights or weeks, as astronomers track the object's motion and measure its brightness changes. These observations allow them to calculate the comet's orbit and determine whether it's making its first visit to the inner solar system or returning after a previous passage. Some discoveries prove to be particularly exciting objects, making their first journey from the distant Oort cloud on orbits so elongated that they won't return for thousands or even millions of years. These long-period comets offer glimpses of materials that have remained essentially unchanged since the solar system's formation, preserved in the cosmic freezer of deep space. Others turn out to be short-period comets, returning visitors whose previous appearances may be documented in historical records or previous astronomical observations. These objects allow astronomers to study how comets change over time as they make repeated approaches to the sun, gradually losing material and evolving in response to solar heating. The international nature of comet discovery creates a wonderful sense of global collaboration. When a new comet is spotted, the discovery must be reported to the Minor Planet Center, the organization responsible for cataloging small solar system bodies. Observers around the world then contribute additional observations, helping to refine the object's orbit and confirm its cometary nature. The naming of comets follows traditions that honor their discoverers while providing systematic identification. Each comet receives a provisional designation based on the year and order of discovery, followed eventually by a permanent name that typically includes the surnames of up to 3 discoverers. This system ensures that credit is properly given while maintaining scientific organization. Amateur discoveries, though less common than in previous decades, still occur regularly enough to keep the field exciting. Dedicated observers using modern equipment and techniques continue to find comets that escape detection by the automated surveys. These discoveries often involve objects in regions of sky that the big surveys don't monitor as carefully. The equipment used by modern amateur comet hunters would seem miraculous to previous generations of astronomers. Digital cameras can detect objects far fainter than the human eye. Computer software can process and analyze images with precision that was unimaginable just decades ago. And global communication networks allow instant sharing of discoveries and observations, yet the fundamental skills remain unchanged. Successful comet hunting still requires patience, persistence, and intimate knowledge of the night sky. the ability to distinguish subtle differences in the appearance of celestial objects, and the dedication to spend countless hours scanning star fields, where discoveries are rare and false alarms common. The psychological rewards of comet hunting extend beyond the possibility of discovery. Many observers find deep satisfaction in the methodical process of surveying the sky. The quiet hours spent under the stars and the growing familiarity with celestial landmarks that comes from repeated observation. It's a pursuit that connects modern astronomers with centuries of predecessors who shared the same sense of wonder. Seasonal variations affect comet hunting, as different regions of sky become visible throughout the year. Spring and autumn often provide the best opportunities when the ecliptic plane is favorably positioned for evening or morning observations. These periods also coincide with times when many comets are approaching or receding from the Sun, making them more likely to show detectable activity. The development of specialized techniques has improved the efficiency of comet hunting. Some observers use blink comparators devices that rapidly alternate between images taken at different times, making moving objects immediately obvious. Others employ digital subtraction methods, where computer software removes all the stationary objects, leaving only things that have changed position. Weather plays a crucial role in comet hunting, as observers need clear dark skies for their searches. Light pollution from urban areas can make faint comets invisible, forcing many hunters to travel to remote locations or limit their searches to brighter objects that can be detected, despite less than ideal conditions. The rise of astrophotography has democratized comet observation, allowing amateur astronomers to capture images that rival those produced by professional observatories. Just decades ago, modern digital cameras can record details in comet tails and comas that provide scientific value, complementing professional observations. Social media and online communities have transformed how comet hunters share their discoveries and coordinate their efforts. Instant communication allows rapid confirmation of new objects, while online databases provide access to historical observations and orbital calculations that help identify whether a suspected new comet might actually be a previously known object, returning the study of very long-period comets. Those with orbital periods measured in centuries or millennia presents particular challenges. These objects may have been observed only once in recorded history, making it difficult to predict their future behavior or even confirm their true orbital characteristics. Some may actually be making their first and only visit to the inner solar system. Hyperbolic comets, those on escape trajectories that will carry them out of the solar system entirely, represent the most extreme cases. These objects provide tantalizing glimpses of materials from the outer reaches of our cosmic neighborhood, materials that will never return once they depart on their journey into interstellar space. The classification of newly discovered objects can sometimes prove challenging, as the boundary between comets, asteroids, and other small solar system bodies becomes increasingly blurred. Some objects show subtle comet-like activity that's only detectable with sensitive instruments, while others may alternate between active and dormant states. The role of serendipity in comet discovery remains significant. Despite all our technological advances, many of the most interesting comets have been found by accident during observations intended for other purposes. This highlights the value of maintaining broad surveillance of the sky, rather than focusing too narrowly on specific targets. Professional astronomers often discover comets while conducting other research projects, studying distant galaxies or searching for supernovae, only to notice a fuzzy object moving through their field of view. These incidental discoveries remind us that the universe is full of surprises for those who take time to look carefully. The future of comet hunting will likely involve even more sophisticated, automated systems capable of processing vast amounts of data and identifying subtle patterns that indicate cometary activity. These systems will complement, rather than replace, human observers whose intuition and pattern recognition abilities remain valuable for spotting unusual objects. The upcoming Vera Rubin Observatory, with its enormous camera and rapid survey capabilities, promises to revolutionize small object discovery, potentially finding thousands of new comets each year. This flood of discoveries will require new techniques for processing and analyzing data, as well as international cooperation to handle the sheer volume of new objects. Space-based observatories offer unique advantages for comet hunting, as they can observe continuously without interruption from weather daylight or atmospheric effects. The James Webb Space Telescope and other advanced instruments are opening new windows into comet composition and behavior, providing data that complements ground-based discoveries. The search for interstellar objects represents a particularly exciting frontier in comet hunting. These visitors from other star systems are extremely rare, but offer unprecedented opportunities to study materials formed around different stars. Each interstellar detection provides a sample of another planetary system delivered directly to our cosmic doorstep. Citizen science projects are expanding opportunities for amateur participation in comet research, allowing dedicated observers to contribute meaningful observations using modest equipment combined with careful technique. These collaborations between professional and amateur astronomers continue to enrich our understanding of these ancient wanderers. The preservation of dark sky sites becomes increasingly important for comet hunting, as light pollution spreads and makes faint objects more difficult to detect. The protection of natural darkness benefits not only astronomers, but also the broader ecosystem and our connection to the cosmic environment. As we continue to develop more sensitive instruments and better analysis techniques, we're discovering that the population of small objects in our solar system is far richer and more complex than previously imagined. Each new comet adds to this growing census, helping us understand the structure and evolution of our cosmic neighborhood. The gentle persistence required for successful comet hunting embodies some of the finest qualities of scientific inquiry. The patience to wait for discoveries, the care to verify observations, and the humility to accept that most searches end without success, yet continue anyway, driven by curiosity and the knowledge that each clear night brings new possibilities. Tonight, as you look up at the stars, remember that somewhere among those points of light, there may be a comet beginning its long journey toward the sun, carrying with it messages from the earliest days of our solar system, waiting patiently for some dedicated observer to notice its subtle motion and welcome it into the catalogue of known wanderers. The search continues, as it has for centuries, driven by humanity's endless fascination with these cosmic visitors and our desire to understand our place in the vast dance of celestial mechanics that governs the universe. Each discovery, whether made by sophisticated robot or dedicated amateur, adds another thread to the tapestry of knowledge we're weaving about these remarkable objects. These wandering ice giants continue to surprise us with revelations that challenge our most basic assumptions about what it means to be a comet in our solar system and beyond. In recent years, astronomers have begun to recognize that some of these objects may actually be refugees from other stellar neighborhoods entirely, carrying within their frozen hearts the chemical signatures of distant suns and alien worlds. The discovery of interstellar comets represents perhaps the most profound expansion of our cosmic perspective, since we first realized that comets themselves were visitors from the outer darkness. When an object arrives in our solar system, traveling on a hyperbolic orbit, one that will carry it back out into the void, never to return, we're witnessing something truly extraordinary, a messenger from another star system that formed around a different sun under conditions we can barely imagine. The first confirmed interstellar visitor was spotted in 2017 by astronomers using the Panoramic Survey Telescope and Rapid Response System in Hawaii. This elongated tumbling object, initially thought to be an asteroid, showed the mysterious acceleration typical of comets, yet displayed none of the expected outgassing or tail formation. It was as if the universe had sent us a riddle, wrapped in an enigma, streaking through our cosmic neighborhood at tremendous speed. What makes these interstellar wanderers so fascinating is how they connect us to the broader galactic community. Every star system likely produces its own population of icy bodies during planet formation, and gravitational interactions occasionally eject some of these objects into the space between stars. They then spend millions or billions of years drifting through the cosmic deep until chance brings them close enough to another star system to be captured temporarily by its gravitational embrace. When we observe an interstellar comet, we're essentially receiving a sample delivery from another world, a cosmic care package that traveled unimaginable distances to reach us. The composition of these objects can tell us about the materials available in other stellar systems, the conditions under which they formed, and perhaps even whether the processes that created our own solar system are common throughout the galaxy. The study of these exotic visitors has revealed both similarities and differences compared to our native comets. Some show compositions remarkably similar to objects born in our own solar system, suggesting that the basic processes of planetary formation may be universal. Others display unusual characteristics that hint at different formation environments or evolutionary histories shaped by their long journeys through interstellar space. The rarity of confirmed interstellar objects makes each detection precious. Most pass through our solar system so quickly and at such great distances that we have only brief opportunities to study them before they disappear back into the void. This has led to proposals for rapid response missions that could intercept these visitors while they're still within range of our spacecraft, providing unprecedented opportunities to study materials from other star systems up close. The search for interstellar objects has also highlighted how much we still don't know about the space between stars. These regions, once thought to be empty voids, are now recognized as complex environments filled with dust gas magnetic fields and apparently a steady stream of wandering objects ejected from their birth systems and traveling between the stars like cosmic nomads. Some scientists speculate that interstellar objects might even serve as vehicles for transporting life between star systems. If microorganisms could survive the harsh conditions of interstellar space, protected perhaps within the interior of icy bodies, they might seed new worlds with the ingredients for life. While this remains highly speculative, the discovery of organic compounds in comets makes such possibilities seem less far-fetched than they once did. The technological challenges of detecting and studying interstellar visitors have spurred innovations in observational astronomy. New survey systems are being designed specifically to spot these fast-moving objects, while they're still far enough from the Sun to be studied in detail. Advanced computer algorithms sift through vast amounts of data, looking for the subtle signatures that distinguish genuine interstellar visitors from the much more common objects native to our solar system. The future promises even more exciting discoveries as our observational capabilities continue to improve. The upcoming Legacy Survey of Space and Time is expected to detect dozens or perhaps hundreds of interstellar objects each year, transforming our understanding of the population of wandering bodies in our galactic neighborhood. Each detection will provide new insights into planetary formation processes around different types of stars and the complex dynamics that shape stellar systems throughout the galaxy. As we've learned more about these cosmic wanderers, both local and interstellar, we've also begun to appreciate their role as agents of change in planetary systems. Comet impacts have shaped the surfaces of worlds throughout our solar system, delivering water organic compounds and energy in events that may have been crucial for the emergence and evolution of life. The late heavy bombardment period, roughly 4 billion years ago, represents one of the most dramatic examples of this process. During this time, the inner solar system experienced an intense shower of asteroids and comets that may have delivered much of Earth's water and organic material, while simultaneously creating the conditions necessary for life to emerge and flourish. Modern studies of impact craters on the Moon and other airless bodies provide windows into this ancient bombardment, revealing the intensity and timing of these events. Each crater tells a story of cosmic collision of energy released and materials redistributed across planetary surfaces, in processes that continue, albeit at much reduced rates today. The recognition that comets may have played crucial roles in making Earth habitable has profound implications for our understanding of life in the universe. If similar processes occur around other stars, then the ingredients for life may be widely distributed throughout the galaxy, carried by wandering ice giants that serve as cosmic gardeners, planting the seeds of complexity wherever conditions allow. This perspective transforms our view of comets from mere curiosities to essential participants in the grand story of cosmic evolution. They're not just beautiful visitors that occasionally grace our skies, but active agents in the ongoing process of planetary development and perhaps biological evolution throughout the universe. The study of comet chemistry has revealed an astonishing diversity of organic compounds, including many that serve as building blocks for biological molecules. These discoveries suggest that the chemical complexity necessary for life may arise naturally in the cold environments where comets form, making these objects potential repositories of prebiotic chemistry, waiting to be delivered to suitable planetary surfaces. Some researchers have even proposed that comets might harbour actual living organisms, microbes that could survive the harsh conditions of space protected within the icy matrix of comet nuclei. While this remains speculative, the discovery of extremophile organisms on Earth, living in conditions once thought impossible, has expanded our conception of where life might exist. The implications extend beyond our own solar system to the countless other worlds that astronomers are discovering around nearby stars. If comet bombardment is a common feature of planetary system evolution, then many of these distant worlds may have received similar deliveries of water and organic compounds, potentially setting the stage for the emergence of life in environments we can barely imagine. As we continue to study these ancient wanderers, we're also developing new appreciation for their role as time capsules, preserving materials from the earliest epochs of solar system history. Each comet nucleus contains a frozen library of information about conditions in the primordial solar nebula, the disk of gas and dust from which all the planets eventually condensed. The isotopic signatures found in comet materials provide particularly valuable clues about solar system formation. Different isotopic ratios can tell us about the temperature and chemical conditions that existed in various regions of the early solar system, helping astronomers understand how our cosmic neighborhood evolved from a simple disk of debris into the complex collection of worlds we see today. These studies have revealed that the early solar system was far more dynamic than once thought, with extensive mixing and transport of materials between different regions. Comets formed in the outer reaches contain minerals that could only have crystallized at high temperatures near the young sun, suggesting that powerful processes redistributed materials throughout the developing system. The continuing evolution of comets as they age and lose material through repeated solar encounters provides another window into solar system dynamics. Each passage near the sun strips away layers of material, gradually exposing deeper regions that formed under different conditions. This ongoing process of erosion and evolution means that comets are constantly changing, providing snapshots of their internal structure and composition over time. Some comets have been observed to split apart during particularly close approaches to the sun, creating families of smaller objects that follow similar orbits. These fragmentation events offer rare opportunities to study the internal structure of comet nuclei, revealing details about how these objects are constructed and how they respond to the stresses of solar heating. The dark regions observed on many comet surfaces tell stories of repeated solar encounters where organic compounds have been altered by radiation and heating, creating complex chemical changes that gradually darken the surface. This weathering process affects how efficiently comets absorb and reflect sunlight, influencing their behavior as they approach our star. And so, dear fellow stargazer, we reach the gentle end of our cosmic journey together, having traveled from the frozen depths of the Oort cloud to the warm embrace of our inner solar system, following these ancient wanderers as they dance their eternal ballet through space and time. We've seen how these remarkable ice giants connect us to the very dawn of creation, carrying within their hearts the building blocks of worlds, and perhaps even life itself, while continuing to surprise us with dark comets and interstellar visitors that challenge everything we thought we knew about our celestial neighborhood. Sweet dreams, and may your own dreams be filled with the quiet wonder of these patient travelers who remind us that we are all part of something infinitely vast, beautiful, and mysterious. something infinitely vast, beautiful, and mysterious.